So hello everybody, welcome back. I'm going to finish up this chapter today with types of fog. So we looked at types of clouds, we've looked at types of condensation. Fog, again, is just another type of condensation, and there are several types. We could break these down into finer and finer categories, but we're going to look at 4 different types of fog. Advection fog. Remember, fog is just a cloud at ground level. So an advection fog, okay, everybody knows by now what convection is. Convection is the vertical motion of air. Advection is the horizontal motion of air, and you probably know that better as wind. So most fogs will get broken up by wind, but an advection fog actually needs wind. Not a high wind, but just a little breeze to waft it through. So advection fog is common along the coast of California. It involves warmer air moving over a colder surface. And off the coast of California, we have a cold current called the California current. And warm, moist air coming from the Pacific moves over that cold current. And through conduction, that air cools down as it's in contact with that cold ocean water. It cools down, and of course there's going to be water vapor in that air, so it condenses. And we end up with a sea breeze that kicks up in the afternoon, and that fog, sometimes you hear it referred to as the marine layer. That marine layer gets wafted into onto the coast. And I'll show you some pictures of that in a second. So it involves a cold current. So in the northeastern part of the U.S., we have a Labrador current, which is a cold current, and the same kind of thing happens. So Maine, the northeastern part of the U.S., Nova Scotia and Canada, and these areas are known for the fogs that they have. And again, it's because of cold ocean currents that are offshore. Then a radiation fog forms when the ground cools off on cold, clear nights. We talked about this as a temperature inversion when we looked at what happens in the troposphere. So the ground cools off, and the air in contact with the ground is going to cool off. And if there's any water vapor in it, that water vapor will condense. And here in the valley, we call that a tule fog, which is named for the type of vegetation that grows in these low-lying wet areas. Tule fog in the Central Valley. It's a type of radiation fog. Then an upslope or orographic fog, that's a fog in the mountains. We saw how when adiabatic cooling takes place, we end up with clouds that form. Well, it all depends on your perspective. If you're driving in it, if you're in the Sierra Nevada and you're driving in this condensation, you would say, wow, I'm in a fog. But if you're in the valley looking up at the mountain and you say, oh, it's cloudy up there. So it just depends on where your location is. So orographic fog. And then steam fog. A steam fog is caused by the evaporation of warmer water into the cold air above a water surface. So if you've ever seen a fog over Lake Tahoe or over Folsom Lake, that's a steam fog. So let's look at some pictures of these. The typical touristy pictures of San Francisco that show the Golden Gate Bridge kind of obscured by fog, that is an advection fog. San Francisco is known for its microclimates, where it might be warm and sunny on one street, you walk to the next street and you're freezing to death because of the fog. Then this is another view of it. Again, advection. The wind is bringing that fog on shore. There's another view. You see Sutro Tower in the distance there, so the fog isn't impacting that area. And this is a radiation fog. Again, here in the valley, we call that a tule fog. And you can see that it's a shallow fog. The air above it is totally clear. That's because it's in the warmer layer. And remember, one of the things we need for a fog or condensation to take place is cooling temperatures. So the temperature is cooled at ground level, but not in the air above it. Let's skip that. Here's a satellite view of the valley. And you can see that fog is almost filling the valley. This is this little round circle right there. That would be Sutter Buttes. So the top of Sutter Buttes is sticking up out of the Thule fog. And then this is orographic fog. Here's the wind, here's the air moving up the mountain, and condensation is taking place as it adiabatically cools. And then here on this side, it's the windward side, or sorry, the leeward side of the mountain. So the fog is disappearing over here as the air sinks and compresses and warms. So we don't have the cooling temperatures that we need on this side of the mountain. And this is Gulf Coast of Florida, and you see we don't have mountain barriers here. We have these condos and hotels that are lining the beach, and they're acting as that barrier. So here comes this warm air, warm moist air off of the Gulf, hits these big towers, and it adiabatically cools, so we get a fog. And then over here you see it disappearing because the air is warming as it descends on this side of the mountain. Look at that. That's a perfect picture. I love this picture. Then this is a steam fog. Usually early in the morning, see the sun coming up, we see a fog, plenty of water vapor above the water surface, and we know we get our coolest temperatures around dawn or so. So the water vapor in the air has condensed as a result of the cooling off. As the sun rises, then we would say that the fog burns off. Really, the fog is evaporating because the air temperature is getting warmer. So a steam fog. This is a steam fog on Loch Ness in Scotland. See how the fog is freezing on the trees, on everything. So again, the water would be warmer than the air. So there's water vapor escaping into the air. That air has cooled down. So we have a fog that forms. This is steam fog over Lake Berryessa. I was driving to school one morning and through these farm fields, and I looked over, perfectly clear everywhere except for that fog bank up there. That's where Lake Berryessa is located, right in that notch in the mountains. So that would be a steam fog. Well, where do we end up having the most fog occurrences? Well, most common in coastal areas that are close to a cold ocean current, so the west coast where the California current is, and as I stated before, the New England coast where we have the Labrador current. Also common around the Great Lakes and the humid Appalachian Mountains. This is a map showing the frequency of fogs, and you can see these areas in red are where have the most fogs. Right here is where I grew up. And we had really foggy mornings, especially in the summertime. In the desert regions, we don't expect as much fog because not as much water vapor in the air. This area here, if you can see let me get a pen here and, no, let me do something else. Hold on. One of these days I'll get this all figured out. Okay. Right there. That area is called Cape Disappointment. There are over 200 days a year that have fog in that area. It's in Washington State. All right, now do I have to get rid of this pen to move my slide? Sorry, folks, I'm just asking myself these questions. I know you all can't help me. That's too bad. I need all the help I can get. Okay, so that brings us to rain. Okay, we've got fog, we've got clouds. Now how about some rain? How do we get rain? Well, there are two ways that we get rain. One is called the collision coalescence process, and this one is really easy to understand. It's where cloud droplets get large enough to fall out of the cloud under the influence of gravity. Think about that, that water molecule. It has a positive and negative side to it, polarity. So in a cloud, you have these water molecules that are sticking to each other through these, unlike charges, they stick to each other and they can get large enough. And when they get large enough to fall to the ground, then we call that rain, of course. Then there is another way that rain can be formed. There was always this question, well, okay, how does rain, if it's collision coalescence, if that's the only process at work, the collision coalescence process, how do we ever get rain in areas that aren't in the tropics? Because once we get high up in the clouds, it's going to get really cold up there. So the cloud is going to have ice crystals and water molecules, but sometimes just are liquid water molecules, but sometimes it's just too high to even have the water existing as a liquid. So the Norwegians, who were really big in the early 1900s in weather theory, one of their meteorologists came up with what's called the supercooled droplet theory. And this says that inside of a cloud, there are going to be ice crystals, but there are also supercooled droplets in a cloud. These are actually water droplets that are well below the freezing temperature. And you might be thinking, well, how can that happen? If it's well below freezing, how are these things still liquid? And it's because they're so tiny. The smaller the surface area of something, the harder it is to freeze. So what happens is these supercooled droplets start sticking to the ice crystals, and the ice crystals get large enough to fall out. So in areas like where we live and in higher latitudes, rain actually starts out as snow, but as it falls through the atmosphere, it comes into warmer layers of the atmosphere on its way to the ground, and it ends up melting. So our rain basically forms as snow to begin with. If it doesn't melt, then we have snow that makes it to the surface. We hardly ever have that here in Sacramento. So types of precipitation will depend on the size of the drop. We have many different terms for rain depending on the size of the drop. Sometimes you hear the expression drizzle or mist. Then snow is composed of ice crystals. Sleet will form as rain falls through freezing temperatures in the atmosphere, and the raindrop freezes and hits the ground as sleet, little ice pellets. Not to be confused with this next one, freezing rain and glaze. Freezing rain and glaze form as a result of liquid water freezing when it hits a cold surface. This is where we have these ice storms. Everything is coated with ice. Sidewalks, buildings, mailboxes, cars, you name it. The rain is frozen on everything. Power lines are dragged down. We have power outages when this happens. And then hail. Hail can only form in a cumulonimbus cloud when a raindrop is caught in these updrafts and downdrafts, these violent updrafts and downdrafts that are in the cloud. Raindrop gets thrown up into the freezing section of the cloud. It freezes, then it gets caught in a downdraft and it thaws, then gets thrown back up into the freezing part of the cloud where it freezes again. So if you've ever looked at a hailstone, it's these little concentric rings of ice. Each one of those rings represents another trip up into the freezing part of the cloud until it gets large enough so that the updrafts can't pick it up any longer, and the downdrafts then will drag it down to the surface. All right, so condensation nuclei are teeny, teeny, tiny. We can't see them. They're microscopic. Cloud droplets are small too. That's why they're able to stay in suspension in the atmosphere. It takes about 1 million cloud droplets to make one average size raindrop. And then this is the supercooled droplet theory, where we have these supercooled droplets that are sticking to the ice crystals. And notice what happens. The ice crystals get large enough to fall out of the cloud. So most rain actually forms as snow and then will melt on the way to the ground. All right, this keeps doing this to me. Let's see. So, I don't know what that means. No, I don't want to do that. Bear with me, please. And let's see if I can get out. There we go. So this is a cumulonimbus cloud. It's clouds of vertical development, the violent weather makers. So there are updrafts and there are downdrafts. The updrafts are what make the cloud grow larger and larger. The downdrafts are where the warm air is cooling off, and these cold downdrafts will blast out of the cloud, and then they can warm up and as they get closer to the surface, and then we have updrafts. So it's just a series of updrafts and downdrafts. The updrafts are what feed the cloud. That's what keeps it growing larger and larger. So we get these raindrops that form, and they get blasted up into the freezing part of the cloud, and then they get caught in these downdrafts, and then get caught in another updraft, go up to the freezing part of the cloud until the hailstone gets large enough to fall out of the cloud. If you've ever been driving down the road and you're in a rain cloud, but it's clear, you're in the updraft part of the cloud. And then if you're getting pounded on with rain or with a hail shower, you're in the downdraft part of the cloud. So I do have a story about this dude, but I can't tell you about it now. And look at this. I hope this doesn't show up when you all are viewing this, but those little marks that I made, they won't go away. There must be some way to get those done. Anyway, who cares? So this is an ice storm. Everything is coated. Every twig, every branch, this is a pine tree, all the needles are coated, so everything gets heavy. Power lines don't stand a chance. These trees are bending over. Look at these power lines. So it's understandable how they get so heavy that they come crashing to the ground. This was from an ice storm that hit in eastern Canada in the 1990s. And not only did you have power lines like this that were broken, but the big transmission towers were broken too. The ice accumulated on them, and they couldn't stand the weight, so they just crumpled like pickup sticks. Here's another view of them. And then again, this is hail formation. Let's look at a hailstone. Hailstorms usually happen in the summertime, spring for us normally. So the stuff that hits the ground, it will melt fairly quickly, and it's just a good idea to pull over to the side of the road, because until you do, it's like you're driving on ball bearings, because they're these little ice pellets, but they don't hang around long. That was driving through Nevada in August. There was a hellacious hailstorm, and this is what those hailstones can do. Cars don't stand a chance against them. There's a cornfield pulverized from hailstones, and this poor kid, I don't know whether he did that on purpose or not, but he is bruised and contused. If you've ever been caught even in just small hailstones, it hurts. They hurt when they hit your body. So he has been just mangled. Look at all the welts on his body. And this is what they look like. Look like a little onion. So there was a nucleus, that was the start of all of it, and every one of these layers indicates a different trip up into the freezing part of the cloud. That used to be the largest hailstone on record, fell over Coffeyville, Kansas in 1970, but then that one beat the record. Let me just do something here for a second again, because I can't see how much it weighed. It weighed almost 2 pounds, and it was about 8 inches in diameter. So you would not want that thing hitting you on the head. And it's a really a bunch of hailstones that glommed together and then fell to the surface as one. So how do we measure precipitation? It's pretty easy to measure rain. Standard rain gauge uses a little funnel to collect the rain, and then there's a cylindrical tube that has measurements on it, either in centimeters or inches. And we can also use radar to measure the rate of rainfall. Snow has two measurements, depth and the water equivalent. So the snow has different characteristics depending on where it falls. We in the West, we get a drier snow, powder is what they call it out here, and skiers love it. In the East, our snow is wetter, and it ices over very easily. So skiing in the East is not such a, I mean, people do it, of course, but it's the stuff out West that dedicated skiers like to ski on. It has more air in it. So the water equivalency in snow will vary, but the general ratio is for every 10 snow units, you can convert that to 1 liquid water unit. So if 10 inches of snow have fallen, then that would be equal to 1 inch of liquid water. If 10 feet of snow have fallen, then that would be equal to 1 foot of water. And we have people from California Water Resources that do snow depth measurements three or so times a year in the Sierra. They have a transect that they will use to measure the snow. That's our water for the year. That's our reservoir. So it's pretty crucial to know how deep it is. And then I'm going to leave you with this: why you shouldn't drive on flooded streets. You never know what might be in the water. Ha ha. All right, that's it for now. See you next time.